Have you ever experienced a circuit behaving erratically or a component unexpectedly failing, even when your calculations seemed correct for its forward operation? It is a common challenge that often points to conditions outside the diode's intended operating range. One truly crucial consideration for diodes is peak inverse voltage, or PIV. This represents the maximum reverse bias voltage a diode can safely withstand without suffering electrical breakdown and permanent damage. Understanding and properly accounting for PIV is absolutely essential for the long-term reliability and stability of any circuit employing diodes. The core mechanism behind PIV relates to the diode's behavior under reverse bias. When a diode is reverse biased, a depletion region forms and widens, blocking current flow. As the reverse voltage across the diode increases, the electric field within this depletion region intensifies. If this reverse voltage exceeds the diode's PIV rating, the electric field becomes so strong that it causes a sudden and dramatic increase in reverse current. This phenomenon is known as avalanche breakdown or Zener breakdown, depending on the diode type and voltage level. This uncontrolled current flow generates significant heat, leading to irreversible physical damage or even catastrophic failure of the diode. To integrate this understanding into practical design, engineers must carefully consider the peak reverse voltage that a diode will encounter in its application. This involves identifying the maximum negative voltage swing in alternating current circuits, as seen in rectifiers, or potential transient voltage spikes that could momentarily appear across the diode. A common practice is to select a diode with a PIV rating at least 1.5 to 2 times greater than the expected peak reverse voltage to provide a sufficient safety margin. This buffer helps to absorb unexpected voltage fluctuations and ensures robust operation. An insightful detail for designers involves distinguishing between maximum repetitive reverse voltage and non-repetitive peak reverse voltage. The former refers to the highest reverse voltage a diode can endure repeatedly without degradation, often specified for a sinusoidal waveform. The latter, however, refers to a single, transient voltage spike that the diode can withstand for a very brief duration without failure. Furthermore, incorporating protection mechanisms such as transient voltage suppressors, or TVS diodes, in parallel with the main diode, can be an excellent strategy to shunt harmful voltage spikes away from the primary component. By meticulously considering and designing for the peak inverse voltage, you are not just preventing immediate failures, you are fundamentally enhancing the robustness and longevity of your electronic circuits. It ensures that your diodes operate within their safe limits, protecting against the hidden dangers of reverse voltage breakdown, and ultimately leading to more reliable and predictable electronic systems.